Hello, everyone. Thank you for joining today's ELISA seminar. We're very delighted to have Pete Brink, who is the principal consultant for software-intensive systems and a distinguished member of technical staff at UL Solutions, to give us a talk on introduction to requirements engineering. Without further ado, Pete, take it over.
Thank you. Thank you, Min. Greatly appreciated. And so, good morning, good evening, good afternoon to everybody on the call. I know this is, you're taking time out of your day to attend this, and I appreciate that. Um, I'll give you a little bit of introduction to myself. I've been in the industry now for about 38 years, coming maybe almost 39. Um, I've spent a lot of time doing embedded systems development for the most part, a lot of safety critical development on things like jet engine control systems and things like that. However, I did also do a lot of embedded systems development for during the early days of the internet, creating devices that could communicate on and could communicate across the network and do things like fixed function devices like print servers and cable scanners and things like that. I then worked at Intel for 18 years, where I learned a lot of different technologies. And what the way I say it is, I also learned how not to do software at Intel. Um, and I say it that way in particular because I worked in a lot of different groups and I had a lot of different empirical experiences, and some of them were better than others. And all of those empirical experiences led me to this understanding of the nature of the software engineering process and software engineering in general. So some things of note is that while I was there, I led an all-volunteer team to create a software engineering curriculum, which we did. We created 40 classes and got them all online and recorded them and so on and so forth. And as a consequence, I became involved in several documents like the Software Engineering Body of Knowledge and the Software Engineering Competency Model from the IEEE Computer Society, as well as becoming a member of ABET. So I don't know if people can see it, but ABET is the Accreditation Board for Engineering and Technology, and it is an organization that goes and evaluates university level engineering programs. So I became a software engineering program evaluator for ABET. And this year we didn't actually visit a university because they withdrew their application, but it's my 8th year of doing this. I've been at UL. Done a variety. I've always been doing the same job, but I've been promoted and was in a managerial capacity. My current title is that of a principal consultant, and I was recently selected to be part of what they call the William Henry Merrill Society. William Henry Merrill was the founder of UL about 125 years ago. And I was selected to be a distinguished member of technical staff, which is not a fellow. So I'm one level below that. Um, I've been at UL now for about 6 years. So with that, let's dive into requirements engineering. And I will click here. I may actually, I'm going to turn on my laser pointer so that if anybody if also feel free if you want to ask questions. I think we're set up to ask them online. I do have my question open, and so if you want to ask a question and it's related to a specific slide, then by all means go ahead and type it in, and I will attempt to answer it during the presentation rather than at the end, just because I think it's probably more relevant. So we'll be covering a variety of different topics here. Um, Really, right off the bat, why write requirements in the first place? Then a basic overview of what the requirements engineering process looks like, and what the things that we perform during each one of those phases. A brief introduction to a methodology about how to write requirements, writing them effectively, really. And then, of course, the challenges that are associated with it. And the challenges vary according to what environment you're in. So, of course, open source represents its own set of challenges that they may be similar, but then have a lot of distinctions between what we might do in an embedded system or a safety critical environment or a highly secure environment as well. Okay, so one of the first questions, I actually asked this question during interviews. So if I end up interviewing any one of you, you'll know how to answer it from now on. So when I ask this question, how do you know when you're done with your design and your development? Really, how do you know when you're done is how I ask the question. And the most common answer I get is software is never done. And my response to that usually is, okay, well, if software is never done, imagine you're on an airplane and you look over at the engine on the side of that aircraft and you recognize that there's software inside the controller on that engine. And I ask the question, do you want that software to be done? And most of the time they answer yes. So then I reiterate the question, how do you know when you're done? And then I don't get any answers. And that's at least in part because this is not a concept that most of the people I talk to have ever thought about before. So we have to come to this realization that we have in an engineering process, there is a specific methodology that we can follow that demonstrates that the software is done. And that is by having a set of requirements that we develop the software to. And then when we're done, we have a set of tests where we can prove that those requirements have been fulfilled. And really, this means we have only the software that we set out to build. There's no dead code, there's no additional code, there's no Easter eggs, there's no nothing in there that allow us to go through and do this evaluation. And this has its own analogs in basically any type of engineering. Because when we build bridges or cars or airplanes, they all do have a set of requirements that we need to develop to. So that there's a sort of understanding. So if we don't build the bridge to its requirements or to its expectations or to its specifications, then it's probably not going to hold up. And of course, then that begs the question, what are the types of requirements that we can ask or that we can look at? Well, and of course, it varies then considerably by which environment we are targeting. So when the fundamental basics of requirements are that they really serve as an agreement between parties. Um, so this means the architects, the systems engineers, the people who are coming up with what the set of requirements are, have to come up with and be able to specify that in such a way where the people who are doing the work have an understanding that there's full understanding of what it is that the requirement actually means, what the expectations for it are, and then when we're done, how we can actually prove that that requirement is complete. So we do that by writing them down. And of course, language inherently is an imprecise thing. It means that we have to have some way of specifying them in a rigorous format such that we, the writers of it, can have confidence that the people who are reading them have a full understanding of what it is that they are receiving and what the expectations are that go with it. So we can write these requirements. They can go to external customers, and this happens quite often in many industries. So if we look at aviation and at automotive, most of the time the people who are building the airplanes and the cars are not the people who are actually building the devices that go on them. They farm that out. They send it to a tier one or to a supplier. So it's important that they have an understanding that the integrators, the OEMs, have an understanding of what it is that they are specifying about that device that they want their supplier to build for them. And that's why they write requirements for it. But by the same token, we can also have internal requirements. And so these may be a little bit differently specified, although certainly if a company is big enough, they can have their own suppliers that are still within the bounds of that same company. But there may be a lot of things that we have to do. So what we call hardware in the loop testing, for instance, I find that the testers often are the best people at this because they have a fundamental understanding of what needs to be done in order to test the product, in order to get it out the door, which means that they then need to have a good understanding of what the requirements are so that they can build tests to demonstrate that the product is actually complete. So that's a sort of that's the thought model that we have to have when we think about when we think about what we're doing when we're writing these requirements. When we write requirements, we want to capture what the system has to do, what the system must do, because without that, it's not a requirement. If we put in things that say, I've seen a lot of things that say the system should do this, and I'm going, well, that's not a requirement, because if it should do it, that kind of means that it's optional. Kind of means that you can choose to do it or not, and that's very difficult to test, and it's very difficult for the person who's receiving that requirement to understand what it is that they're actually supposed to do, whether or not they're supposed to implement it. They can also specify how well the system must do it. So this is where we start talking about constraints. So having detection algorithms that detect at 90% plus, having constraints that say you must fit within this amount of RAM, you must execute your foreground loop within 20 milliseconds on this caliber or this speed processor. So there's a whole host of different things that we can consider when we talk about how well. Most of the time, those are not really involved in the actual functionality of the system that we're developing. They are defining the constraints of the system as we know it. And they can be thermal, they can be physical, they can be mechanical, vibration. There's a whole bunch of different things that we can consider when we go through this. Um, Most specifically, and this is a pattern, and this is a thing that I want people to avoid, is that requirements do not capture how to do it. I see a lot of people wanting to write requirements that basically say, write the code this way. And really, if we do that, I mean, you can do it, and it does actually produce the code that you wanted, but that kind of implies that you wrote the code already and then wrote the requirement around it. So if we write the requirement specific enough that it tells the person what to do, but vaguely enough that we don't tell them how to do it, then that it doesn't constrain them with regards to them coming up with an innovative solution to how to actually solve this problem. So keep those things in mind as you're looking or endeavoring to write the requirements that you're coming up with. So if you want to capture how to do something, put it in the design. And this is really the imperative, because honestly, the design is a response to or an answer, a capture of one instance of how we solved the problem that the requirements set forth in front of us. We have different categories of requirements. We can have functional requirements, which basically give a description of what the system is supposed to do. It can include this nominal functionality. We include here the safety requirements, but arguably there are many different types of capabilities that we might want to specify here. So we want to specify clearly what the nominal functionality for the system that we're developing is. But if there are safety constraints or security constraints that are associated with it, then we capture the requirements that are associated with the safety and security as well. And then we have non-functional requirements. And I don't really like using the term because non-functional, because it kind of implies that they don't function, but that doesn't actually make sense. What these really are they describe characteristics or quality attributes of the system that we're intending to build. It can be a performance constraint, it can be a security, it can be a usability constraint, it can be like we talked about, a physical or thermal constraint for the system that we're developing as well. Um, there may be other things. So for instance, if there is a requirement to use a particular operating system, if there's a requirement to use a particular vendor, well, some of those things may get included here as well. Excuse me. So we have different requirements. I'm covering it from a safety perspective, at least in part, because that's a lot of what we do. So the non-safety requirements are capturing what the nominal functionality for the system that you're building is. When we talk about safety requirements, most of the time they are defining either a safety mechanism that's going to it's going to look for and capture and prevent faults from becoming failures. And a lot of times those faults are hardware faults, but it can also be situations where the software malfunctions. And it can be something as simple as just by having a watchdog timer on the system that you're building. So it's not like this is some exotic solution. It's just a terminology for how we describe it. Um, What I will say though is that when we talk about safety requirements, they still have to conform to quality criteria that we have for any requirements. And so the quality criteria basically apply to everything. And in fact, I created a document that is available in the ELISA repository that goes through and talks about both a process and a set of criteria that you can use to evaluate documentation in general, but certainly you could also use that to apply to requirements that are available that you've written. There are different types of, I think I've covered most of these already. So we have non-functional and functional requirements, but we can also have constraints that are associated with regulations that we need to conform to. So we have in Europe, there's the new UN ECE. It's R155 and R156, which are for security and software updates. In the US, we have the Federal Motor Vehicle Safety Standard, or FMVSS, which describes a whole bunch of different things that constrain the developers of a vehicle and say that there are things that you must do. So, for instance, now all cars must have backup cameras. And very soon, there's going to be a new FMVSS that all cars must have automatic emergency braking. So, this is one of the ways that regulations create jobs. Safety mechanisms, I talked about these a little bit. But safety mechanism is basically a solution, a technical solution to detect and mitigate or tolerate faults, or control or avoid failures to maintain intended functionality or achieve or maintain a safe state. And I know that's a mouthful, but basically what it's saying is that we have to do something if in the event of a failure or in the event of a fault, that we have to do something either to prevent that fault from expressing itself as a failure, or we have to put the system into some kind of degraded mode so that it prevents that situation from occurring. Um, a safety mechanism, you can either transition to a safe state or that you are alert the user. Sometimes it's just telling the driver, hey, it's the check engine light that comes on your dashboard and says, hey, there's something wrong. You should do something to prevent this from becoming or further becoming a problem. Okay, so we have a basic understanding of what the nature of requirements actually are and why we might actually want to put them in place. So there's a basic process flow that can be associated with them. And it's what you would expect. You know, we don't just write you don't just write the requirements and expect that that they're going to be right the first time. Let's just put it that way. So, in this instance, we start with requirements. We start at the start, obviously, where it says that, which says start. But then we have a thing called requirements elicitation. And elicitation is where we go talk to the stakeholders. You go talk to the people, the customers who are going to be using the product that you're developing. In the case of open source, this may not be possible, but it might be possible on a mailing list to go through and elicit a set of expectations about the system or the operating system or whatever it is that you're developing and come up with what people want and why you might want to do it and capture that information. The key criterion here, though, is to recognize that the users don't actually know what they want. So they can tell you what they want, but then you have to reinterpret that. And that's what the analysis and validation is all about. So we have to reinterpret, we have to go through and analyze what the customers asked us for, and then specify those requirements to capture and then deliver what they needed as opposed to what they asked you for. So then at the end of that phase, actually, there are some builds on this page. So that's gathering the requirements from the stakeholders. So assessing, negotiating, ensuring correctness of the requirements. So we're going to go through and specify them. We're going to write them all down. We're going to talk to the stakeholders. We're going to have reviewers that go through and look at the requirements that we've written and make decisions about whether or not they accurately capture what it is that the stakeholders originally requested. And then we go through and write them down. This is a much more formal process. And in fact, in the next section of this, we will talk about one of the processes that we can follow for writing the requirements. So we go through and create the written specification. And then we assess the requirements for quality. So as part of the review, so this verification here, this is one of the methodologies. We have the criteria that we can use to evaluate the requirements and decide whether or not what we've written is good enough. And if it is good enough, then it's one, it's satisfied all of the quality criteria that we have for the requirements themselves. And two, it's essentially captured enough information in the requirements that we can start doing the rest of the development work, that we can feed that information into our development process. And so we can do the architecture, we can do the design, and we can do the coding based upon the information that was in the requirements that we captured in the first place. And let me stress right here, in no way do I intend for this to be a quote unquote waterfall-like process. The process of doing all of this is you're constantly testing. So as you get into the architecture, design, and coding phases, if you discover that there's a problem with the requirements, then it's imperative upon you to go through and address that, because making sure that the requirements are correct is the only way that we can actually prove at the end of this whole thing that the requirements are actually have been fulfilled. So if as part of our design work and our implementation work, we discover an error, then you go and fix it. So this is inherently an iterative process. And so as a consequence, it fits with any type of iterative development that you might want to do, whether that be agile or just, the regular iterations. In embedded development, we always did iterations based around the maturity of the hardware, because agile didn't work quite as well in that environment necessarily. This could fit with releases that you do in a particular for like the Linux kernel or one of the Zephyr releases as well. So overall, overarching all of this, we do also want to make sure that we have requirements management. Which means that as we do releases, that we have an accurate set of requirement that reflect what the release was that we were doing. And what we found is actually it's a fairly easy, it's a fairly good thing to use GitHub and Markdown to capture the requirements. Now, it doesn't give you the traceability that you might get with a requirements management tool, but it is free and it is something that's available. And I believe actually there are a couple of documents, StrictDoc and Basil, that are both under development right now, that will end up doing requirements management for the open source community with a tool that was developed for the community itself. So this verification, we're going to verify the quality of the requirements. And then at the end of the whole process, when we get into our product verification and validation, we're going to create and perform a set of tests. And of course, this is obviously we have potentially unit tests that we execute against the code. We have integration, we have component tests and integration tests, and we have customer acceptance tests. The customer acceptance tests are really where we're looking at requirements throughout all of that testing, but the requirements, the customer acceptance is really where we are, focusing on those and making sure that the original set of requirements were fulfilled correctly. That this is called verification by analysis because we're not actually executing any tests. And of course, verification by test because that's where we are executing the tests. There are a variety of different characteristics that we can use to evaluate the quality of the requirements. They have to be unambiguous, comprehensible, atomic, so on and so forth. I'm not going to read them all to you. On many instances, I've actually seen verifiable and testable included in the set of characteristics. So verifiable then to me means, can we review it? Is it comprehensible? Is it something that where we can understand this and actually perform an analysis against it? And then another bullet is testable. Can we write a test? Is it feasible to write a test that that demonstrate that this requirements has been completed? And of course, implementation free. Um, that's talking about individual requirements, but of course then we have groups of requirements, and so we want them, at least according to the automotive safety standard ISO 262, they want them to be in a hierarchy. So that means we have higher level requirements that flow down into lower level requirements, whereas we go to the lower level ones, they sort of refine the details of what the higher level requirements have told us. The most important thing right here is complete. We want to have the requirements fully specified as a group such that we can determine that there's enough information. Maintainability and traceability are a constant concern because if we make updates, we want to make sure that the requirements are correct. So this is where I talked about having the requirements in the same database as the source code and even the documents. So that's an important aspect of the whole thing. Um, Traceability is always going to be a problem. We want to be able to show that any architecture design or coding work that we've done and tests that we've done trace back to the requirements. Maybe just making a reference to the requirements number, because it needs to be uniquely identifiable as well. Right. It needs to be allocated to an item or an element, so a component. It has to have some sort of unique identification that remains consistent. It has to have a status, and it has to have an appropriate syntax. And it can be a natural language or a natural language supported by diagrams. And so we'll talk a little bit about those um, coming up here in the next few slides. If it has a safety integrity, it should have that safety integrity associated with it. If it has a security associated with it, then we probably want to keep that associated with it as well. So there are some additional possible attributes that we can associate it with it given the context or the environment that we are using the requirement in. One of the first things that we can have is informal notation. Informal notation is basically just writing the requirement as natural language, which is fine. It's not supported by any documentation, any diagrams or anything like that. It's the lowest level of complexity. It's the highest risk of misinterpretation. So the possibility that somebody misinterprets is high, which is why why when we'll talk about the syntax of it coming up. So it's easy to write, but it's not easy to write well. So we can then, there's a thing called semi-formal notation, which is where what we do is we enhance the natural language by using diagrams. And it can provide it provides additional material to provide context for what the requirement is intending to fulfill. So the additional rigor, the advantage is that it's less prone to misinterpretation. But of course, the disadvantage is it takes more time. You need to be added an additional level of effort to creating these documents and the diagrams to enhance and support the requirements themselves. And then here's an example of semi-formal notation. So we have a requirement, and then we have some descriptions of a diagram and what it's intended to do when shifting up or down. So this is using Simulink, which isn't necessarily available. So that's maybe part of the problem with open source is that these tools aren't necessarily available to you. And if you want to try and use something like Lucidchart or Data.io, they don't necessarily lend themselves quite as well. They do have UML support, and I've done a reasonable amount of UML in um, in Lucidchart, but it doesn't have a diagramming. It doesn't. There's no way to execute this model here as part of Lucidchart. Let's just put it that way. The last of these I haven't, the only place I usually see formal notation is in things like satellites, where it's really, really difficult to be able to make modifications to it. If anybody remembers when the Hubble telescope had a problem, it involved sending another shuttle trip out to the Hubble to be able to, make repairs. So we do formal notation when is less opportunity to correct problems that are associated with what it is that you're intending to build. So in automotive, formal notation is not, and it's not recommended specifically. Formal notation I mean, the implication here is that they have a tool where you can do formal evaluation and formal verification of the requirements in the tool itself. So there are tools that you can use to do these things. I don't recommend those. Um, we are running short of time, so I'm going to go through these quickly. So we have a requirement here that's not very good. So what's the problem with it? It's ambiguous. It doesn't tell us what system it is. Doesn't tell us what status messages are. And what it doesn't tell us that it's incomplete. And it says at regular intervals, but it doesn't tell us how often. So it says at least 3 seconds. Would 10 years be okay? So there's a lot of improvement that's possible here. So we rewrite it to say, we define what the system is. The tire inflation monitoring system shall store inflation pressure values in the vehicle management system registry at intervals of 3 seconds plus or minus zero point 0.1 seconds. So, right, we've corrected all of the errors up above without specifying what the implementation is, and whoever is going to take and architect this has a firm understanding of what it is that they need to do. So what's wrong with this requirement? So we have electrical wiring harnesses shall be protected from physical damage and should include brief but intuitive descriptions of wiring functions and intended connection devices. Once again, it looks okay, but there's a lot of problems with it. And it has a very glaring thing right here that I really should highlight as part of all of this. This is a keyword. If you ever see this "and" in a requirement, you know that it's not atomic. The requirement speaks of both protecting the wiring and labeling the wiring. So we know this is at least two requirements. So to improve it, we've actually then written 3 requirements that satisfy all of it. The last one um, basically defined, I looked up what MIL Standard 681 is, and it's a color coding scheme that specifies how how you should wire the wiring harness so that it complies with this, and it becomes obvious who's for somebody who knows the color scheme or has a chart can actually go through and interpret what the signals actually are. So So to verify requirements, we ask first and foremost, are the requirements compliant with the criteria? Should be an S right there. Is there enough information in the requirements to create the architecture? Are the requirements consistent with higher level safety requirements, if that is something that you have? Are they compatible with any higher level design? So in the instance where we go from systems design to software design, it may be that there are a set of system requirements that sort of constrain or set up the properties for the software that you're coming up with, software requirements. And are the requirements consistent with any system level external interfaces? It may be, so there's some play, like I said before, there's a lot of opportunity for there to be flexibility and to iterate between these things, because obviously as we write the requirements, if they are not compliant with the external interfaces, then they need to be updated. However, it may point out that the system level external interfaces need to be updated as well. So when we do reviews, the safety standard actually defines 2 different methodologies. They amount to the same thing. The walkthrough is significantly less formal than the inspection, but both of them involve getting somebody or some additional number of eyes to come in and look at the set of requirements that you've created, to evaluate them and make a decision about whether or not they are enough to be able to move on. It helps. So I did this with Kate Stewart for the Zephyr project. We went through hundreds of requirements and ended up rewriting a significant number of them just because it was that additional set of eyes, and we were trying to capture them based upon the criteria that we're using to evaluate them to tell us what constitutes a good requirement. Um, so Writing requirements. So I will introduce the topic here of ears. So ears is the easy approach to requirement syntax, and it was developed by Alistair Maven and his colleagues at Rolls-Royce in 2009. So for people who don't know, Rolls-Royce makes jet engines. And so in the UK, it's one of the divisions, and they sat down. So it's a fairly formal and fairly deliberate process that we go through to come up with the requirements when you're working for something like a jet engine, because by its nature, it is very, very safety critical. Um, so ears to find then a consistent syntax. I really, really like it because there is a consistent syntax, we can actually write parsers. I haven't done it, but I should, is we can write something in Python to go through and parse a requirement, and then evaluate it to see whether or not it is something that is, if it complies with the syntax first and foremost, but we can go through and evaluate it. So we have a rule set. We have preconditions, we have triggers, included features, system name, and the system response. We have a generic syntax that's associated. While precondition, when trigger, the system name, shell system response. And this captures the nature of how, especially functional requirements that we might want to write. So from that, we can come up with a different set or a wide variety of different types of requirements that are associated with it. The first are ubiquitous requirements, which are the sort of generic ones that we expect to be applicable everywhere. And that is the system name shall system response. It's obvious. It's always applies. It's always something that we have to pay attention to. State-driven, event-driven, optional features, each one of these things, we're essentially adding a precondition to the ubiquitous response that tells us whether or not that requirement applies in a given situation. So for those of you who didn't see the answer, but in this instance, Greg Shu asked a question at the very beginning of this whole thing, and he says, "How do you write a requirement that is only applicable for a given release type?" And so and then he gave the example of a release versus a debug mode version of the software. Well, we can have an optional feature where debug mode, the system name shall system response. So we have an answer right here for how we constrain the set of the requirement itself to be applicable in only a given situation. And of course, we can increase the complexity of all of these and combine multiples of these syntactic patterns in order to create this. So how do we consider? So let's keep in mind when we're writing requirements. I gave some examples of both good and bad requirements earlier in the presentation. So generate requirements. This is where we start. When we don't know, we create a set of requirements that define the scope of the system. So these are going to be constrained by information that we've received from our stakeholders. We describe the full system description, but we don't go too deep. We give, it's essentially what a very high level architecture would look like. And we're trying to define the functionality that goes into each one of the blocks that we've defined in that architecture. We're writing requirements for those blocks. As part of this process, you want to go through and define what you're going to write and what you're not going to write. So it's important to recognize that sometimes it may not make sense to define it to the nth level of detail. So if there are already some things that have been decided, then capture that information up front and don't write requirements about it. Decide when to write the pieces that are necessary. I like to call this lazy evaluation. So don't do it. Don't do it, or maybe more specifically, don't do it yet. If you don't know the details or you don't have an idea of how something is going to work, maybe go into a prototype and make a decision based upon what that prototype and then write the requirements. So it's not exactly lazy evaluation, but certainly it's lazy requirements writing from that using that terminology. Create the details at the appropriate time. And if you're writing from a safety context, keep risk reduction in mind. So when we look at safety and security standards, they are fundamentally risk evaluation frameworks. So keeping in mind that we want to reduce the risks. And of course, it is always possible to iterate. So revisit previous step as you learn more, as you do the architecture, as you figure out what does and doesn't work, revisit the requirements to make sure that they are still aligned. And this is kind of the art of writing requirements, because if you write it vaguely enough that you can still fulfill the requirement without having to change it, that is the ideal situation. And of course, I stress that it is possible and recommended to work requirements in an iterative model. So it begs the question, how much detail should we capture as part of the requirements themselves? So I would argue that the level of detail that you put into the requirements varies according to the criticality of the system that you're developing. So if you don't put in enough detail, you've increased the risk. And some of this risk is not risk that you can alleviate by testing specifically, because there are situations, there are perhaps tests, unless you are doing exhaustive testing, there are tests that you don't even know that you need to run that will make the entire system fall flat. And of course, too much detail is increased investment. The more time you spend writing requirements and doing design, the less time you have for implementation and testing at the back end. In my experience, it makes sense to spend a decent amount of time on doing some of the design work up front, because the more work on requirements and design that you do, the easier the coding is. And that's just my own empirical observations from having done this quite a few times. Safety in general requires more detail because we really don't want to have any escapes, shall we say. We don't want airplanes flying out of falling out of the sky. We want them flying, not falling out of the sky. So what are the challenges? Traceability. Traceability is always a problem. It helps a lot if you have a tool that allows you to do that for you. So as you're writing tests, as you're doing design work, there's an inherent association that you can create and fix between the requirement that you wrote and the design work and the testing that you're performing against that requirement. Um, Documentation is okay. Things like Excel and Word or Google Docs, or even Markdown, they're difficult to version effectively. Markdown is okay. GitHub allows you what I would really like is an actual documentation tool like Google Docs or Word, with a front end on it that allowed you to manage it the same way that Git allows you. So you can do feature and development branches, and then merge the changes in when you're done after it's been approved, and merge in changes from the baseline if somebody else is making modifications at the same time. But right now that I haven't seen where that exists. I mean, except in straight text, using something like Markdown. And so that's there, but of course traceability is still an issue in that instance as well. Although it has an advantage that if you do the change management of your requirements coordinated with the source code management, then you're guaranteed that whenever you do a release, the requirements match the source code. Product complexity. So as products get more complex, it becomes more and more difficult to write requirements and do architecture for them. So fundamentally, design work is a complexity management tool. So the better job or the more effort we put into the design, we're stressing complexity and simplicity, or stressing simplicity as a mechanism to manage the complexity, we can reduce that as part of as how we go along. And then, of course, the product release. So how do we manage that effectively? And people are working like this right now. So certainly the SBOM work with SPDX is something where I think product release may become quite a bit simpler as we go through all of this. So now we can get to the questions. And I see that there's a series of them in the Q&A already. The first, or actually, it's just in the chat, so they weren't in the Q&A. So the first of them is from that says, "Can you tell why formal requirements are not recommended in automotive?" Um, I I don't know specifically why they are not recommended in automotive. I think it's from it's honestly, I think it's from a risk perspective. So there isn't a reason to go beyond semi-formal in automotive because of the risks that are already being managed by the development process that's included in the automotive industry already. And so as a consequence, they don't need to do formal requirements as a part of that. Um, so the next one here, why can't this be categorized as performance or non-performance, non-functional requirements? Um, so I'm sure that it can be. The examples that we showed were not necessarily of a particular type of requirement. And in fact, oftentimes the formal versus, not formal, sorry, functional versus non-functional requirements end up being intermixed. So it should be an expectation that you have all of them in there. But it's a recognizing the different types of requirements that you need to write, and how you want to capture that information. Formal requirements in general are easier to write well, because then we have the opportunity to actually, because we can look at them from a testability standpoint. Whereas when we talk about performance or non-functional requirements, a lot of times what we have to do is test them, we have to evaluate them via analysis. So did we stay within the thermal boundary? Did we stay within the mechanical constraints? Can we support this level of vibration? So there's a test there as well. But we can do a lot more of it, or sometimes we do a lot more of it via analysis than via deliberate tests. We have another question here. For the first example, what is wrong with this requirement? At what point should the requirement be decomposed? Splitting out the storage and rate versus keeping them together. Um, they are separate requirements, because when we had that keyword "and" in there, it meant that it wasn't a requirement. It's important to recognize that when we want the tests, we want the requirements to be atomic, because really we want the requirements to express one thing. It's a lot like the single responsibility principle when we're doing design work. When we design something, we want that thing that we're doing, that we're developing, to do one thing and one thing only. Because the minute we try to make it do something else, suddenly we've changed the functionality and we've made it more difficult for us to express what it is that it's supposed to do. So if we capture what that requirement means as a single atomic requirement, we can both verify it and test it for that one thing that it's intended to express. So you asked the question when. Arguably, there should be a higher level requirement, that those derived requirements that we would create from that they would both point back to. And that higher level one probably expresses something um, about the fact that the system that we were talking about just needs to report this information. So we would create a requirement that says it needs to report this information, and then we derive requirements from it that tell us how often and the kind of information that it needs to contain. And of course, traceability would be included there as well. Um, the next question. LaTeX sounds like what you described as a tool for version text that could also include graphs or tables. So that would be great. The only thing I've heard about LaTeX is that people either love it or hate it, and I would have no experience with it myself. So maybe it's time for me to start diving in and start looking at how to use it effectively. But thank you. That's good feedback. We can certainly start making that including that as a suggestion. Um, Are there any hands raised? No. Okay. So Min said if you'd like to speak.
Yeah,
Um, Sorry, go ahead.
I was just gonna say I actually, yeah, I allowed the ones who posted questions, I've given
Okay.
you permission to speak. So if you would like to speak, just unmute yourself and then you can speak.
Okay. Sounds good. We have another comment here that says Sphinx and Sphinx needs can be considered for requirements tracing and and configuration managed. I'm assuming CM, do you mean configuration management and not change managed items? Because sometimes those are different things. In the safety standard, they're actually listed out separately. Okay. Greg has a question. If ears verb where is used for feature dependencies, how are dependencies on hardware variants expressed? Um, so I think you just answered your question. So if we can go back and look at the ears statements, the criteria, the optional features, keeping in mind the to me this is I think it's still an optional feature, or we can make a complex one that has the optional feature that describes the hardware specifics, and then either unwanted behavior or state or ubiquitous requirements that are based upon that constraint that's associated with it. And I'm hoping that that answers your question.
The situation I'm struggling with is in one case, we can be talking about the presence of an external fuel tank for an aircraft.
Okay.
Software hasn't necessarily changed. And the second case, we're looking at debug versus release builds, where they apply at very different stages of the solution development.
Okay. So the applicability, I agree with you, but the applicability. So keeping in mind that we're talking about a hierarchy of requirements, right? And the first of those, where you talked about having an external fuel tank, is really applicable at the system level. And so that um, that the knowledge that that external fuel tank is there would cascade down through all of the requirements that are then applicable to that version of the aircraft itself. Whereas when we talk about the debug versus release mode, we're really talking about the software for a specific release that goes into a specific electronic control unit on the aircraft itself. So, arguably, we would have both. We would have a we would have a where condition that describes the external versus internal fuel tank, or external or not external. Um, and then we would have then four requirements, one for each of the different instances of the fuel tank, but then we'd have a debug and release version for each of the external or non-external fuel tank.
Thank
That
you.
make sense?
Yes, thank you.
Okay. Uh, Martin asked the question, what I wanted to say, aren't there in aerospace several projects and efforts to actually achieve formal requirements? Then this would be a fundamental difference between automotive and aerospace that I did not know of. So I do know that formal requirements are a thing. I have not seen them specifically. And most of the time, when I've seen aerospace requirements, they've gotten to the semi-formal state. When I worked in aerospace, we did not use even semi-formal. They were all simply written as informal requirements. It was all text specifically. And actually, that the experience that I've had through the years, the vast majority of the requirements that I've seen written are informal requirements, which is why I was so excited about ears, because it then actually created a much more formal syntax around the informal requirements, which made them, to me, significantly more rigorous than they had been in the past.
Mhm. So maybe I can now I can speak. Can you hear me?
Please,
Right. So
bitteschön.
This Martin speaking. Great. So
Yeah.
thank you very much for this explanation. Essentially, in this is in research actually a big topic actually to achieve. First of all, checking requirements automatically because there are many of
Yes.
them. You know that for sure. But also to achieve that you maybe can automatically create test cases out of them directly on all of the levels of your development. So just as a comment, so I found it really quite interesting to see that that in automotive this is a bit different. And
Yes, it is.
I agree with you in practical projects. I have also rarely seen formal requirements yet.
Right. That's
Okay.
and that's why I said that the only place I've seen the formal ones were in instances when you really had to use them
Mhm.
specifically.
So
Yes,
thanks. Great. Thank you.
you're welcome. Gab. Of course, it's when it comes to open source software, requirements usually are defined on top of pre-existing code. Do you have not KPIs, key performance indicators that you use to determine the granularity of the requirement allocated to an open source component? If that is the right one. So is it granular enough? You may have perfectly written requirements that are not sufficient to characterize the different possible behaviors of the software implementation of these. This is not something I've done me personally when I did my development work. Usually the requirements predated. So keeping in mind the requirements predated the software, but the requirements were then based upon knowledge that we had gained through essentially what was a prototype. So we had gone in and cleaned up an existing project and then taken the knowledge that we'd gained about how that thing worked and then wrote a set of requirements about it and implemented it a different way. So from that context, uh, So the problem with writing the requirements based upon the code is that there may be things like you described that the code does that we cannot adequately describe, which leads to me to two conclusions, two potential conclusions. One is that maybe we need to write another set of requirements, or two, maybe we need to refactor the code and simplify the code in such a way where it can be expressed in a requirements in effective manner. So I don't know that either of those is an equitable solution right now, but that's how I come out. That's how I look at it specifically. Gab, did you want to elaborate?
Yeah, yeah. Thanks, Pete. Yeah, because I mean, I agree. No, the problem is that traditionally, the software development model in safety is based on the V model, that is a waterfall model, and also the requirements engineering practice have been developed using the mindset of requirements coming before anything else, right? So you first do requirements, then you do
Right,
design, then you do code, and eventually during the verification activities, you massage this, you fix things that you have done wrong, right? So, but
right,
the challenge is that with open source software, there is a code first approach, and usually the code is able to do way more things compared to the use case of interest, right? For which you specify requirements.
agreed.
So yeah, so to this extent, it is now, in my opinion, the challenge is, to find the right trade-off between, requirements and design specification and code,
Right,
so that it becomes manageable and also acceptable from a safety point of view. And
agreed. So
I
arguably
know,
what we're arguing for is a blend, right? What we would like to see is not requirements only first and not code only first, but some combination of that. Does that sound right?
it, yeah, yes and no. I mean, it will be more likely low-level requirement code first, and then every integrator will chime on top, right? Depending on
Right.
the specific use case. So, but again, so an open question would be, should we reconsider, the requirement engineering practice to have, maybe new practices or different ones that would be more tailored to a code first approach, right?
S- Maybe.
Yeah.
I mean, I don't know that I'm amenable to it necessarily because I've had such success doing some amount of design requirements and design work first that really refines the code that you write. You write the code a lot more efficiently if you have some sense of what it is that you're actually doing, that what you're setting out to do in the first place, as opposed to the sort of the iterative it's not quite right approach because I'm what I'm striving for is efficiency in the development process. And let me reiterate here as well, because you said it, you said the waterfall model, and I know we're basically out of time, and I appreciate everybody staying on this amount of time as well. Um, but the waterfall model doesn't mean really, well, I mean, it means something to most people. But when we actually go look at what the waterfall paper originally said, it described specifically the model that I just described, which is that it's inherently this iterative process. That's what so it was, you can look it up on the internet. It's the guy name, his name is Dr. Winston Royce. It was published in August of 1970. So 55 years ago, he knew and published the fact that we needed to do iterative development. The fact that people looked at the paper that he wrote and didn't go past the first page is not his fault. So we recognize that. I recognize that. So it's important. This is the stuff you learn when you create a software engineering curriculum. Let's just put it that way.
Mhm.
So I know there are more questions. I unfortunately do have to drop for another meeting. Min, do you have anything else that you need to do as part of closing this out?
No, this is, yeah, thank you very much, Pete, for giving us this very engaging talk, and appreciate everybody, yeah, asking really good questions. There's just one comment from Willie, just mentioning there's a tool called StrictDoc that you
Yes, I mentioned StrictDoc actually.
Yep. And there's actually a session about this at the upcoming ELISA
Awesome.
workshop in Munich. I'll just put the schedule in the chat. People can check it out. We'll, share the information when they become available as well.
Excellent.
So with that, thank you everybody for spending an hour here, and thank you very much, Pete, for giving us this talk. And if you're interested in what other events coming up on hosted by ELISA, please go to elisa.tech website, and we look forward to your participation. Thank you.
Bye, everyone.